Hi, good afternoon or good morning, everyone. My name is Vitor Quito. I'm a postdoc at Iowa State University and Ames Lab. And today I'll be talking about emergent symmetries in one-dimensional, strongly disordered interacting systems. This is a topic of research that I started to work on during my PhD, and I continue throughout my postdoc. So let me start by saying what are the topics that I'll be covering today. So first, I will talk about broken versus emergent symmetries. Then I will give a brief introduction to disordered systems. These are two important ingredients for our results that come later. Then I will talk specifically about random spin chains. And I will introduce how to handle such a system that is via this so-called strong disorder renormalization group. That is also known as SDRG. And finally, I will present our results on emergent symmetries. In random SON symmetric chains. And I will finish by talking about some future possible directions of research. So this is how I'm structuring the talk. So the first point is about broken symmetries versus emergent symmetries. Okay, so broken symmetries are a very familiar concept in physics, both in high energy and condensed matter. This concept is basically everywhere, and it's quite common concept. The idea is that the ground state of a given Hamiltonian or a Lagrangian is not invariant under all the symmetries that were originally present in the Hamiltonian or the Lagrangian. So, and this is, as I was saying before, this is true everywhere. An example that is interesting to us is a crystal. So a crystal breaks translation symmetry in time, translation symmetry in space, and the atoms, let's say, organize in this given structure. Another example, just to connect with my colloquium last week, is about magnetic systems. So for example, if we consider a triangular lattice, as we did in my colloquium, at low enough temperatures, the system develops this 120 degree order. So this is called 120 degree order. That breaks the SU2 symmetry that the Hamiltonian, there was an explicit symmetry of the original Hamiltonian. For us, for this talk today, I will be mostly focusing on low energy physics. So typically these ordered states will appear, or they appear as low energy, low temperature instability. So these are phases that appear at low temperatures. And for almost every symmetry, there is a model that breaks it. So you can construct or often engineer systems that, given a symmetry group, you can find states that are going to reduce that symmetry by lowering to a group that is smaller than the original symmetry group of the Hamiltonian or the Lagrangian. And this is a very useful way of classifying phases of matter. By the symmetries that are broken and by the symmetries that are left. So broken symmetries are a concept that is around for quite some time. In today's talk, I want to go in the opposite direction. I want to talk about emergent symmetries. So emergent symmetries, I will define it as a low energy sector of a system that is more symmetric than the high energy one. So as we lower the temperature, let's say, the ground state and the excitations are more symmetric than the bare symmetry of the original Lagrangian and the original Hamiltonian. And a natural way of understanding this is in terms of a renormalization group approach that I'm going to talk now. So the emergent symmetries is we have when the low energy sector is more symmetric than the high energy one. And the natural way to describe it in terms of the renormalization group is to think of a fixed point, and around this fixed point at high energies, we have some operators that are going to break the symmetry of the fixed point. But at low energies, the flow is towards this fixed point. So this is the low energy or low T fixed point. And the assumption is that this low energy fixed point is stable at low temperatures, and it has some symmetry, let's say G, big G. This is the symmetry of this fixed point. And at high temperatures, you have some irrelevant operators here that break this symmetry down to small g, where small g is a subgroup of big G. So that is the mechanism behind emergent symmetries, and it's naturally described in terms of a renormalization group approach, where the fixed point is more symmetric than the physics of high energies, where some operators break this symmetry. In today's talk, I will be mostly focusing on emergent symmetries in disordered systems. There are...
Excuse me, can I ask you a question?
Sure.
Is this the same mechanism that is usually called order by disorder in the classical realm, let's say, that was discussed by Villain in the 80s?
Okay. I think order by disorder is slightly different. So order by disorder is when you have a system and then you have a manifold of ground states that are completely degenerate. And then by bringing quantum fluctuations, you have some type of order. But this type of order that you end up having doesn't necessarily have more symmetries than the original bare Hamiltonian that you had. Doesn't necessarily have to be more symmetric than the original Hamiltonian. In this particular case, I'm assuming that the initial Hamiltonian has a symmetry, and then the low energy fixed point has a enhanced symmetry. I don't think that's necessarily the case when you have order by disorder. Okay. Order by disorder can also lead to something that I'm not talking about it here, that about topological phases. This is, I'm leaving behind, I'm not talking about topological order and topological ordered states. So for now, today, I'll be focusing on just symmetry classification, and in this, for example, the symmetry breaking that I'm talking about here is Landau classification of phases of matter, for instance. There are some examples, several examples of emergent symmetries. One of them in the Ising model, close to the critical point, it presents an E8 emergent symmetry that was actually realized experimentally. So while emergent symmetries are not as common as symmetry breaking states, there are several examples when this happens, when the low energy fixed point is more symmetric than the original Hamiltonian of the model, and some of them have experimental verification. For example, this Ising model. There are several other models. Tarkirical Ising model also presents emergent symmetry. And often the continuum limit of some theories also presents some symmetry that is broken by considering the lattice. So the lattice breaks the uniform translation in space. And by taking the continuum limit, you recover sometimes some of these symmetries. Okay, so in today's talk, I'll be focusing mostly on the effects of disorder. So for now, let me give you a brief introduction about the effects of disorder, because our results concerning emergent symmetries in disordered systems. I'll just give a brief overview. The point is that I want to make is that we often want to avoid disorder, especially in technological applications. But for today's talk, we are going to use disorder to construct some phases of matter that would not exist otherwise. So these are intrinsically disordered phases. And one such example came in 1958 by Anderson about the Anderson localization. So just to give a brief summary of one such example of a phase of matter that only exists with disorder, if we consider a lattice like this, at high enough dimensions and weak interactions, we can describe the energies and the excitations in terms of the momentum. And we have some dispersion like this, that is the energy as function of momentum. And then we set the chemical potential. Let's say if the chemical potential is crossing one of the bands, we have a metal. And if interactions are not strong enough and dimensionality is high enough, this phase is stable. So this is a Fermi liquid type of phase. And we know how to characterize the ground state and the excitation. So in this case, it's a metal. The excitations are going to be electrons moving up in energy. And that's the description that starts with the Bloch's theorem for the clean system. We go to momentum space, we compute all the bands, we fill up the bands, and we have this weakly interacting gas of excitations. But if we start with this system and increase disorder, or if you put some disorder, and by disorder here I represent a collection of random points in space, then this is no longer the case. In fact, there is a critical disorder value in which this system that I'm representing here, the description is no longer valid and the system becomes an insulator, a band insulator. And this is the mechanism of Anderson localization. Or this is the idea behind Anderson localization. And you can draw a phase diagram as function of disorder strength, let's say.
Sorry, one question.
All right.
You said a band insulator? It's not the band insulator.
Oh, sorry, a metal for this case that I said.
No, okay, the Anderson insulator is not a band insulator.
Ah, okay.
You don't fill up the entire band.
Right.
You still fill up out the Fermi energy. But it's
right. It's an right. Oh, yeah. Thank you for yes. It's a disorder-driven insulator. You fill up to the chemical potential. It would otherwise be a metal, but given the disorder, the states are localized, and therefore this is I think this is the what I mean by Anderson insulator. It's an insulator where the states, the description in terms of these extended states is no longer valid. You fill up to the chemical potential, but the eigenstates of your system are completely localized, and therefore, yeah, thanks. That's what I meant by Anderson insulator. And then there is a critical value of disorder WC. So for a small enough value of disorder, it's still a metal, and then it becomes an insulator here. Okay, and this is to exemplify that disorder can lead to very interesting phenomena. In this case, a band insulator having now the eigenstates completely localized and therefore being in this Anderson. Let me put it here: Anderson insulator to distinguish exactly from the band insulators. So you can have band insulators by just putting a chemical potential in the region where there is a gap. This is not what I'm talking about. I'm talking about localizing all the states of the system and therefore leading to this Anderson insulator state. Okay, so this was just maybe one of the earliest and simplest examples of effects of strong disorder. But in today's talk, I will be interested in some other example that are random spin chains. So random spin chains, I will just draw what I mean by a random spin chain here. So we take a one-dimensional system. Let me try this again. So I'll take a one-dimensional system. I will start with a collection of magnetic moments or spins in this particular lattice. And these spins will be connected by some random couplings. So I will call these random couplings J1, J2, J3, J4, J5, J6, J7. Okay, these are some random couplings. And these couplings are chosen according to some probability distribution. Let's say we have a probability distribution P of J here, and as function of J. And just to completely define the problem, so the spins here interact with a Heisenberg type of term that is J3, example S3 dot S4. Okay, and we'll assume for now these are spin 1/2 particles. Okay, spin 1/2 particles. So we just realize a chain by drawing these couplings, all of these couplings here from this probability distribution. We just choose random values. This is typically how we realize, at least theoretically, how we describe a disordered systems. We say we have a given distribution of couplings, and then we have this, when we choose this collection of couplings, we say we have a realization of that disorder. So we just pick up the random numbers. And the main goal here will be to describe the physics of random interacting chains like this one. Later in the talk, I will extrapolate not to spin 1/2 particles, but to other types of spins. But that is our main goal, to describe.
A quick question. Do you assume that there is an average value of J? In other words, for instance, is this like an antiferromagnet where there is some randomness in it? You're assuming the distribution is such that could be either have the same probability of the interaction being ferromagnetic or antiferromagnetic.
Oh, thanks for the question. This I will assume it's not going to order antiferromagnetically. It's going to be some other phase, but I will assume that all the J's are positive. Okay. Other types of phases can be found if you mix positive and negative J's, because then you have competition of antiferromagnetic and ferromagnetic physics. But for today's talk, I will be mostly worried about positive couplings that would otherwise, in a clean system, lead to antiferromagnetic phases. But I will also assume that disorder is strong. So disorder for this disorder is strong. It's not a small perturbation to the clean system. Any other questions?
Sorry, what do you mean by strong here?
The standard deviation is large compared to the average. So the distribution is very broad.
Okay.
But that comes, I will be more precise about it in a minute, because we are going to take advantage of this fact that the disorder is very large. And then that's precisely where I'm going next, when I will go to part 3 and introduce this strong disorder RG procedure. So the main goal here will be to describe the physics of this disordered chain. And for that, I will revisit a technique that was first introduced by Ma, Dasgupta, and Hu in 79 and 80. And many analytical results were derived by Fisher, by Daniel Fisher, in 94. Okay, and now I can say a little bit more what I mean by strong disorder. By strong disorder, the assumption here is that, let's say that I choose a given bond here, J2. Okay, under the strong disorder assumption, if J2, let's say, is very large, it's extremely likely that J1 and J3 are much smaller than J2. And I will use this fact explicitly. So what I mean by strong disorder is that let me write it here, strong disorder means that the standard deviation is large compared to the average. And also, if let's say J2 is the largest coupling, I'm just calling the largest coupling J2, and I will give it a special name omega, then it's likely that the neighboring couplings J1 and J3 are much smaller than J2. We are going to use, in order to develop this RG and characterize the low energy physics, these facts explicitly. So by looking back at the chain that we have here, so if J2 is much stronger than J1 and J3, it makes sense to solve the problem for these two spins, 2 and 3, coupled by J2 separately. So we just remove this particular bond from the chain and just solve it separately. So we're going to solve this problem here. And then we bring back quantum fluctuations to recouple this two-side problem to the chain and see what is the net effect that the quantum fluctuations are going to give us. And this is going to be the basic RG step.
Sorry, this is this just a theoretical model, or is there actually an experiment that can reproduce this kind of system?
Right. So yeah, thanks for the question. This is this type of chains can be realized in quasi 1D compounds in solid state physics. And some of the, so for now I'm talking about random spin half chains, but there are proposals in terms of cold atoms to realize there are cold atoms realizations of chains like this that are connected by, for example, spin 1 chains connected by.
But I'm just asking, how do you engineer, for example, J2 to have no relation to J1? I mean, yeah, I would think that there's some kind of, that if J2 is large, then the one close to it is also going to be large. Just, I mean, how are you going to engineer them to be completely independent?
For example, if you just dope a system, if you have one solid state physics device and you dope it, it could be that the atoms are now displaced randomly. And then you can, the hope is to, if you include correlations between J2 and the neighboring, it becomes a harder problem in the sense that here I am trying to describe everything in terms of the probability distribution of a single variable. Sometimes it is harder than the variables are in fact correlated, and then we need a joint distribution. But theoretically, we are, this is the simplest case, and experimentally by doping, the atoms are going to be displaced more or less randomly, and this is a good approximation.
Okay, thanks.
I will also.
So you're assuming that the distribution, that all of these J's are independently distributed?
Yes, I'm assuming that the J's are independently distributed, yes. So everything can be characterized by a single, the distributions can be characterized by a single variable. I will assume that there is also a cutoff here, omega, to the distribution. So this is the largest possible value. And so the RG procedure, as I described, is going to be first we solve this pair connected by J2. That is assumed to be very large. Well, if it's a spin 1/2 problem, we can just diagonalize it. We get a triplet and a singlet, and we get an excitation omega, an excitation gap omega between the singlet and the excited state. That is a triplet. So this is the first step, solve the two-side problem. And now we don't want to just remove this two-side problem from the chain completely. We want to bring back the quantum fluctuations. And this is done in perturbation theory. And I will tell what the net effect of the quantum fluctuations is. So we have a spin 1 here, and then we have the spin 2 and the spin 3. Recall that these are the strongly connected spins. And then we have spin 4 and 5. So these spins 2 and 3 are going to be frozen into a singlet. So they are forming a singlet. And then there is a connection between 1 and 4. 1 and 4 were originally disconnected, or not disconnected. They were not directly connected. But now there is an effective coupling between 1 and 4 that is given by half J1, J3 by omega. And we, under this assumption, the other spins, let's put it spin 0 and so on. Here J4, here J0. These are not affected by the decimation step. So this is what is called a decimation step. And 2 and 3 are now forming a singlet. They're frozen together. 1 and 4 are now directly connected by a new bond that is smaller than the original J1 and is smaller than the original J2. Okay, this is smaller than the original J1 and J3. J1 and J3 also disappear from this problem. And notice that the topology of the chain is preserved. This is a great advantage of working in one dimension. This technique is very precise and tailor-made to work well specifically in one dimension. It can be generalized to other dimensions as well, but the topology of the lattice will change. And strong disorder, because this step of freezing 2 and 3 into a singlet requires that the neighbors are not comparable to the original to the coupling, the middle coupling here. Otherwise, this singlet approximation would be bad. So in terms of the probability distribution, if we go back here, we see that what we are doing effectively is to remove some weight of the distribution. We are decimating this guy here, that is the J2. We are also removing J1, so I'll put a small hole here in J1, and I will put another hole here in J3. And then we are creating a new coupling that is smaller than J1, is smaller than J3, and is smaller than J2. So I'll just represent this new coupling here. And from this picture, it becomes already clear. I will just maybe delete this part. It becomes clear that as we run this RG, and we run this RG by iterating this procedure that I'm describing here. Clearly, this procedure can be iterated over and over again. It's just now we have new couplings. We have 2 sides are gone, but we still have a connection between 1 and 4, and we can just repeat it over and over again. So, and by repeating it, what we are doing is lowering this energy scale omega, and we are generating couplings that are very small, and they're smaller and smaller and smaller. So at low energies, and by low energies here, I mean low temperatures. If we keep doing it, reducing the temperature, if we have a given system, as function of Jp of J, it gets a distribution that looks like this. It's going to be very singular for J equals to 0. So, and this is what I will call a fixed point distribution. So after we flow for enough time or for low enough temperatures, and what is remarkable is that all or a huge class of such initial distributions. So we start with initial distributions P of J, and almost all of them flow to the same distribution P star of J. So this is the concept of universality.
Sorry, I have a question.
Okay.
So at each stage of renormalization, does P of J is automatically normalized, or do you have to normalize?
No, when we want to write down the flow equation, something that I will not do here, derive the flow equation explicitly, you have to take into account the normalization, because we are, as we see here, we are removing 3 bonds and just putting 1 bond. So there is a term in the flow equation when you write down the RG flow equation that has to take into account the normalization of the distribution, yes. And notice, just to connect with RGs that are not related to this disordered case, that here we have to take care of the flow of a distribution. It's not 1 or 2 couplings. This is a normalization of a flow equation for the entire function. It's a functional type of procedure. So,
sorry, this is a power law?
This is a power law. This is a power. Actually, this was solved by Fisher, and I will write down here what is the solution. The solution is P star of J given omega is 1 by omega gamma, omega divided by J, 1 minus 1 by gamma, where gamma is log of 1 by omega. So the flow is more natural in log variables. So that is why this variable gamma appears. So it is a power law. So it's with this power. And as you notice, the power of the power law keeps flowing until it reaches almost close to 1. This distribution is extremely singular. It's extremely singular for small j.
What happened to the cutoff that you had before, the omega? Do you still have a cutoff?
Yeah, the cutoff is this big omega here. There is a cutoff, always a cutoff.
But I didn't see in the power law, there is no cutoff.
Oh, sorry. Yeah, this is true for j less than omega and 0 otherwise.
Okay.
Sorry, the argument of the log probably needs the cutoff. Yeah,
right. The log, I'm assuming here to be
has to be
1.
dimensionless. Yeah,
Right. I'm just assuming there is some omega 0 that is some high energy cutoff that we usually assume to be 1, but we can just write it here. So omega 0 comes from the initial bare distribution. So the initial bare distribution has a cutoff, high energy cutoff, omega 0. And then we have this natural log variable, gamma, that is the log of omega 0 by omega. And this is the form of the distribution. And this omega keeps running, so we keep reducing it. And this is the form of the asymptotic distribution at low energies. What is also remarkable is that initially we had this assumption that this coupling was much larger than the neighboring couplings, and that's what allowed us to develop this procedure. If we look at what happens at lower and lower energies, and if we calculate the ratio of the standard deviation by the average, this ratio flows with DRG. And at low energies, this goes as square root of gamma, and this actually diverges. Okay, so the disorder keeps getting larger and larger. And therefore, this technique becomes asymptotically exact.
Sorry, a question. So suppose you started with the Gaussian distribution for the initial at the bare level of the Hamiltonian.
Okay.
Then as you iterate, this actually will have long tails, essentially. Is that what you're saying? The distribution is highly non-Gaussian, essentially.
Yes. Let's say that we start with a Gaussian, but all the couplings are positive. Otherwise, we can have
I understand, yes.
Yeah.
So
But
you
then,
make the average sufficiently large so that you don't see the
right.
form.
Yes, it will flow to this. Gaussian is a very nice distribution. It doesn't have any issues. It will flow to this one. The only class of functions that don't flow to this one is a class of very fine-tuned power laws. There are some power laws in which the flux gets stuck, so it doesn't flow all the way to the fixed point, because you cannot destroy the initial power law completely to build this new one. But a Gaussian distribution, large enough, initial distribution, if the initial disorder is large, it will flow to this at low energies. Yes. Okay, so this is the procedure, and now we see that it works well for one dimension. It becomes more and more exact at low energies, and now we can compute some physical properties by using exactly this procedure here. So let's.
Sorry, Vitor, just a naive question, but if you have a Gaussian, isn't the first approximation not true, that the largest coupling, there is likely a coupling very close to it?
So if you have let's say we have a Gaussian that is purely positive, and then there is a cutoff here, right? So in the initial, let's assume that this Gaussian is large, okay? That is the only assumption that we need to make. And then my initial argument here, let me see, where did I? Yeah, let's look here. So this J2 is one value that we get from the Gaussian. It's by assumption the largest one. So it is likely that J1 and J3 will be small. They are, by construction, smaller than J2. It could be that initially for this Gaussian, they are not extremely small as compared to J2. This could happen. There are some rare events in which the neighboring couplings are not as small as compared to the J2. But the point here is that this will only appear in the early stages of the RG flow. If you keep flowing for long enough, the distribution will become extremely singular, and you can calculate the chances of having a neighboring coupling. Let's put it here. So let's see this problem, J2 is assumed to be large, or the largest one, and then J1 and J3. We can calculate as function of, at the fixed point at least, what is the probability of this J1 and J3 being large, or of order of J2. And this probability goes to 0. So the point is, we have to have initial strong disorder initially. Otherwise, we don't expect this to work. We expect to have the physics of, many times the physics of the clean system survives, actually. So this is a very bad approximation and a very bad technique. But if disorder is strong enough initially, then it will flow to a phase that has infinite disorder. And I can say that at this point here, this is going to be a phase of infinite disorder. Infinite disorder.
Sorry, just a clarification. I thought in Fisher's picture, what he imagined was that there will be one particular bond that will have the largest possible value of J. And then the nearby ones will have very low probability to have a comparable value of J.
Right.
Okay, that's and then you sort of integrate out the worst one, and then you look for the next worst one, and so on and so forth. Is that what you're doing? Yeah.
That's precisely the procedure, yes. This is precise. It was developed in the 70s and early 80s by Mahu and Dasgupta, and then Fisher actually went to solve this equation. But that's precisely what I'm doing. The way to iterate is exactly that. You look at the largest one, you assume that there is a small probability that the neighboring ones are comparable to the largest one, and then you solve the problem, and then you get a new chain here, and then you search for the next largest one, integrate over, and repeat the procedure. That is precisely what I'm showing here, yes. Okay, so now we can calculate some physical properties also. By drawing the fixed point distribution as function of J. So we have a power law like this, and then we have a cutoff omega. And we are also going to have some temperature, T. And the assumption is that disorder is so strong that if the couplings are smaller than T, the spins are free. And if J is greater than the temperature, the spins are frozen into singlets. This is a very good approximation for close to the fixed point if disorder is strong enough. Well, if the spins are free, we know how to calculate physical properties. And if they are frozen, we also know how to do that. So it's just a matter of counting how many of the spins are, or what is the fraction of spins that are frozen and what is the fraction of spins that are free. Several physical properties can be calculated by just using this picture. For example, the susceptibility as function of temperature is going to give the number of free spins at that particular temperature, and each spin contributes with a Curie susceptibility contribution. And from the solution of the flow equation, so from this solution of the fixed point, we can just calculate the number of spins that are free, and this gives us 1 by T and a log of T to the half here. Sorry, to square here. Okay, this is how we calculate physical properties.
So, all right, so there's no phase transition then.
No, this model for a spin 1/2 chain with strong disorder, there's no phase transition. We just have one phase. This is the phase. I will draw. This is a good. I'll draw a phase diagram. Let's say as function of disorder. So
sorry, one quick question. Okay. So 1/T is simply the Curie law, right?
Right.
Okay, these are in free spins.
Right.
The log T squared comes from the RG essentially?
Yeah, it comes from, because not all the spins are free. So at a given temperature, if we look at the chain, a snapshot of the chain at that particular temperature, it is a very good approximation to consider all the spins that have couplings that are higher than the temperature to be frozen. So these spins do not contribute with a Curie for the curious.
So essentially, you run the RG until you get to until the scale is the temperature.
That's right. Yeah, we can do that. Yes, we can run until the yes.
Sorry, Victor, before you continue, you keep writing W, but I don't know what W is.
Oh, W, oh, sorry. W is the disorder strength. So let me define it. Thank you for the question. This is disorder strength, which is the ratio of the standard deviation by the average. Okay, thank you for the clarification. For a spin 1/2 chain, at zero disorder, you'll have the clean phase. It's not it can be solved with other techniques of the answer. It presents quasi long-range order, and any infinitesimal amount of disorder here will destabilize the phase, and it will flow to this infinite disorder phase. So in all this region here, we expect this infinite disorder phase. Obviously, in this region here, we cannot treat this problem with the technique that I'm showing here, because the technique assumes that disorder is very strong. But from other techniques, you can construct a phase diagram that looks like this as function of disorder strength. You have the clean system here, and then all the other phases, all the other points here are in this phase of infinite disorder. So this is the only phase transition that we have at this point. And this phase of matter is known as a random singlet phase. We can random singlet phase. And in the random singlet phase, we can have a picture of the ground state. The ground state is going to be a collection of spins, and those spins are forming singlets like this. Notice that the spins forming singlets can be very far apart, and they are actually random in position. So that's where the name random singlet phase comes. So this is the ground state picture. Okay, this is the ground state picture. And the excitations, you can just find by breaking some singlets. So it will be free spins. You break some, let's say that this bond is very weak. So at some temperature, this bond can be neglected. So the two spins are no longer forming a singlet, and the excitations are therefore free spins. And okay, so that is the idea behind this, how to handle strongly disordered magnets. It especially works especially well in one dimension. In higher dimensions, it is not as simple. It can be done, but there are extra complications, and it assumes strong disorder. So that's why I said before, in today's talk, we want to probe the physics of strongly disordered systems. I will now go to our work about emergent symmetries. So is there any other question about what I showed so far?
So again, this is all theoretical, but I mean, are there experiments that verify this kind
Yes,
of? Oh.
there are some experiments. In particular, not in this, I'm not aware of any experiment in one dimension showing this type of physics, but in silicon doped with phosphorus, the phase is believed to be a random singlet phase, even though it's in higher dimension. And also in some iridates, there are materials that in principle that are desirable to realize spin liquid physics. For example, this Kitaev is spin liquid materials, but if disordered, the current understanding or the current conjecture is that they present this random singlet phase physics. It's not so simple to, the flow here is completely in log scale, so it's not so simple to extract crystal clear if this is in the signatures of this phase. It has mild signatures, but so far these are candidates. Silicon doped with phosphorus, some iridates, they are conjectured to present this phase, random singlet phase in higher dimensions.
How about simulations?
Sorry?
How about numerical simulations?
Numerical simulations in higher, in one
in one dimension.
They agree with this picture completely.
How do they manage these logs, the logarithms?
It's not so simple. So, for example, if you do like there, I know some of some DMRG.
Yeah.
approach, it's not so crystal clear, but the agreement is, it agrees well. It agrees well with these logs. If they can do very large system size in 1D, you can do like with the MRG, you can do large system sizes, and then
I assume provided they are in this regime to begin with, where the disorder is strong compared to the average. Otherwise, the crossover may be complicated.
Yeah, you assumed, absolutely, you assume disorder is large, but then you can start coming to this slowly going in this particular direction. The crossovers will start to kick in. So far, nothing was seen in this particular region here. That is the current scenario. There's nothing here. This is, however, I would just point out before also, since there is this question, the phase diagram does not have to be like this. For spin 1 chains, and spin 1 chains are going to be relevant for us. So let me just write for spin 1. There is a phase here in which disorder is irrelevant. That is the Haldane phase. It's protected by a gap. And then we know that disorder doesn't close the gap immediately. There is a critical value of disorder for spin 1, but not for spin half. This is what I showed here is for spin half.
So there must be some kind of a new fixed point then.
For which one? For
the phase transition from the Haldane phase.
Yeah, there is a fixed point, yes. There is, in fact, a Griffiths phase in the middle. So the Haldane gap closes. There is a Griffiths phase that is, you have power laws and you have no gap, and then you have a transition to a random singlet phase.
What is the nature of that transition, or is just simply the Griffiths regime?
It's simply the Griffiths regime. The critical point is of infinite disorder.
I see. So the Griffiths regime begins at some point, or is always present?
The Griffiths regime begins for infinitesimal disorder, very low disorder. There is no Griffiths regime. It's the Haldane gap protects the physics completely. It's still a Haldane phase. And then for intermediate disorder, the gap closes. You have Griffiths type of phase until you reach a critical point of infinite disorder where this physics of random singlet phase.
Yeah, but my question in a sense so that requires a quantum phase transition between the logical phase, which is this Haldane phase, and the random singlets phase.
Right.
So is that phase transition understood?
I think at the critical point, the physics, it is the same. The physics of the critical point is the same physics as the random singlet phase. After when you reach the end of the Griffiths phase, you are at already, the critical point is already at this random singlet phase.
No, I understand, but you said there is a critical disorder where the Griffiths phase begins.
Right, so let's draw it.
Okay, I want to know that critical point. Is that critical point understood? Not the infinite disorder fixed.
Oh, I see. So here.
This is the one that Fisher characterized. Okay.
Right.
So
you're asking about this one here, where let's see, we have the Haldane here.
Yeah.
And then we have Griffiths here.
Yeah, so this is a topological phase for, below WC. And then there is something which is certainly not topological and that flows into the infinite disorder fixed point up to, this Griffith.
I'm not sure if there is a phase transition here actually, or if this is a crossover to a Griffiths phase. There is a critical point here.
Okay, well, fine. So this is what I wanted to know. Okay.
Oh,
so
sorry about
in classical systems. The onset of the Griffiths phase, there is a debate whether that's a phase transition or not.
Right. Here, there's no. I'm not familiar if there is a critical point here. I think it's a crossover to a Griffiths phase. I'm sorry, I misunderstood the question. Here, there is a critical point. Oh, and let me write it just here correctly. There is
the classical systems where the Griffiths regime begins is where you fail to thermalize, essentially. You become, Leticia is the expert on this, not me. Okay, but is where things essentially go wrong. I don't know what is the quantum version of that.
But you could discuss this problem in classical terms as well, right? Because going
Yeah.
from 1D to 2D classical,
Yeah.
then you could
Yeah, but
maybe.
the question is you have to deal with coherence, okay, which the classical problem doesn't. So, so it's an interesting question. Okay, so I'm not sure what is the analog of falling off equilibrium in this case.
Right, I can tell that here, in terms, here there is this, oh sorry, here there is this RG prescription that I just described.
Right, yes.
Here you can also have a modified RG prescription that captures some of the physics of this Griffiths phase. That actually connects, I won't have time to show it today, but connects well with these AKLT states. These are, we can describe this as a deformation, or as starting with the AKLT state. I'll just briefly mention this since there's a, start briefly just with the AKLT state that looks something like this. And then you can describe this group, and then you have a random singlet phase that looks like this, just random singlets. And you can describe something in the middle by allowing these two spins here not to be forming bonds like this, but for example, they can form bonds like this with other spins here. So that's how this RG can be generalized, starting from this AKLT point that is inside the Haldane phase, and then this order, we can just form the state, you start getting singlets with other sites. But I won't have much time to discuss all of this because I would like to move now to our main results about emergent symmetries within this. And in our case, we're going to have emergent SU symmetry in SON chains. And for that, I will consider a chain now that is not going to be a chain of spins, but or it's going to be a chain of spins, but not spin 1/2, but instead these spins will be SON spins. Okay, so initially we were discussing here spin 1/2 and spin 1. These are SU2 spins. So now I'll be describing SON spins, and SON spins are described by the generators of the group that are this LAB. These are the generators of the SON group. And this LAB, they correspond to rotations in this AB plane. So let's say that LAB applied to B gives AI, LAB applied to A gives minus IB, and LAB applied to C gives 0 if C is not equal to AB. So now we are making it a bit more abstract by introducing this other symmetry group SON, but this is how it acts. It's the group of rotations. This is the group of rotations. There are several interesting realizations of SON chains, especially for small n. So for small n, there are some correspondences that are interesting. So for n equals to 2, this corresponds to an isotropic SO2 case. So if you take an SU2 chain and you make the z direction different from the x and y directions, and assume x, y to be the same, you get this SO2 chains. N equals to 3 is SO3, and the algebra of SO3 is isomorphic to the algebra of SO2, and this can be realized as a spin 1, the spin 1 case. In fact, that's why it was good to have this discussion about the spin 1 in the previous case, because the n equals to 3 does correspond to the n equals to 3 corresponds to the spin 1 case, and n equals to 4 is the algebra is isomorphic to SU2 cross SU2, and this corresponds to what is known as the Kugel-Konski model. And in n equals to 6, this is the algebra is isomorphic to SU4, and SU4 spin chains with SUN symmetry can be realized in cold atoms systems. So this isomorphism, this algebra isomorphisms for small n are useful. So therefore, this is not purely a theoretical problem, it can be realized by considering these small n cases. And I will now present the results of how the flow looks like. And for that, there is an important difference as compared to the spin half case that I showed before, is that now we are going to have 2 couplings per site. So in a given bond here, we're going to have 2 couplings that I'm going to call K1 and K2. So a given site has 2 couplings. And I'm going to assume that the ratio of this coupling is fixed. So I'm going to call tan of theta the ratio of K2 by K1. And I will, this is not completely necessary, but just to make it easier to analyze the flow, I will assume that there is no initial disorder in the angle. Okay, there is no initial disorder in this angle.
Sorry, can you explain what are these 2 couplings?
Yes, I will define the 2 couplings here. So when we have the Hamiltonian of a given bond is Ki1, Li dot Li plus 1 plus Ki2, and I will just write it down, Li plus 1 plus 2 by n by 2 Li plus 1 squared. So this is, unlike the spin 1 case, we can allow for this term here, and this is the quadrupole term. So this is the product of quadrupole operators of SON, and these are dipole operators. So it's dipole-dipole interaction and quadrupole interaction. This is what...
So for spin 1, you can also write the term.
You can also write this, exactly. For the n equals to 3 case, it's completely analogous to this one. So the spin 1 follows the same procedure by just setting, by setting n equals to 3 here. If you set n equals to 3 here, you get the spin 1 physics. N equals to 2, you cannot, you don't do it because this term is linearly dependent with the other terms. But for n equals greater than, this correspondence here are good in that sense. N equals to 3 is the spin 1 case. And now we can define, we already defined the angle variable. That is tan of hi is the ratio of K2 by K1. And we can define a radial variable also as the square root of Ki1 squared plus Ki2 squared. Okay, so these are 2 independent variables for each bond. So recall that before we only had 1 variable per bond. Now in each bond, we are going to have these 2 variables, theta and r. But r is going to be random, but not theta, not the initial theta. So we have R1, R2, R3, and so forth. And theta, we'll assume that is theta 0 for all of them. So this is the problem that we can solve.
So this is a simplifying assumption, or
this is a simplifying assumption to start with. It's not required to have this assumption. In principle, we can give some disorder, some width to this theta distribution. It doesn't change much if it's small. I will explain. I think it will going to become clear as I draw the phase diagram. It is a simplifying assumption. It's not necessary, but it makes it simpler to analyze the flow. So just a question, how much time do I still have? I think you're muted.
How much time do you need?
10 minutes, let's say.
Yeah, that's fine. No problem.
Okay. All right, so let's analyze the flow of this problem now. So we draw 2 axes here, and then a circle. Okay. And we are going to draw this phase diagram. The phase diagram now has 2 phases. K2, sorry, it has 2 parameters, K2 and K1 now. And there are some special points in this phase diagram. Again, I will start by assuming that the angle is not disordered. There is a point here, pi by 4, minus pi by 4, minus 3 pi by 4, and 3 pi by 4. These are special points, and these are points that have explicit SUN symmetry. Okay. So these are already points of enlarged symmetry. So SON is a subgroup of SUN, but there are some fine-tuned points here that have this explicit SUN symmetry. And I will show how I have to tell you how the angle flows and how R flows. So let me first, for concreteness, show how these variables flow in one of the phases. Let's say, let me just put the phase boundaries here.
Sorry, maybe I missed the point. N is not fixed yet. N can be anything, right?
Yeah, we are solving for a class. So a given chain will have a fixed N, but this solution that we have is for any arbitrary value of N.
Okay.
So initially we fixed the problem by fixing the group N, and then we construct the generators of that particular group, SO3, SO4, and so on, and then we apply this procedure.
Sure.
This phase diagram will not depend strongly on N, actually. As you can see, I'm already drawing the angles, and I'm not saying that they depend on N. There are some details of this phase diagram that do depend on N. For example, there is a phase here. There's a region here where disorder is irrelevant. This is the generalization of the AKLT points to this. This is a state that is present already in spin-1 chains to this SON chains, and even strong disorder is irrelevant. This state is extremely robust. These details do depend on the value of N, but otherwise this phase diagram is very general.
There are also some angles for which the pure system is integrable, right?
There are some angles in which the pure system is integral. Usually these are, in this language that I'm writing here, I think they are the plus and minus pi by 4 still, because I'm changing variables. But yes, there are some angles here where this system is integrable, yes.
But I think, no, you don't necessarily have SUN symmetry at those points, so it should not be that. I think they have SON symmetry only, they don't have SUN.
You haven't told us yet.
Right.
Pedro, you're discussing the pure system.
Yeah, the clean system.
Yeah, I'm asking for the pure system, yeah.
Yeah, they are SU2 level 3 or things like that. But
Right.
Here the disorder, I don't know. He will tell us.
Right. This is, this point here for the clean system presents this SU3 level 1. It's a critical system. For the spin-1, you also have this Takta-Jan-Babujan point that is somewhere down here, but I don't think, I think you're right. It's not the minus pi by 4 that I have.
But it doesn't play any role in what you are doing.
It does not play any role. I mean, again,
Okay.
the assumption here is that disorder is going to be so strong that unless even strong disorder is irrelevant, these points will not play any significant role here. So the phase diagram will look like this, and then the flow of the angular variable here is to this theta star equals to 0. So now I'm just representing schematically. Let me be more precise about what I mean by this flow here. So we had initially two variables, a variable theta and a distribution p theta of theta. And initially we assume that this is a delta function in a particular value. Okay, not completely necessary. It can be like have a tiny standard deviation, but that's not so important. Throughout the RG flow, this distribution will broaden. So it will broaden something like this until it reaches a fixed point value theta star. And this is what I'm calling theta star here. For example, in this particular case, theta star is 0 for this phase that we have here. So this is what we call angular fixed point. The flow of the R variable, so we are again parameterizing in polar coordinates. The flow of the R value is similar to the flow that I showed you for the spin-1 half case. So you start with a given distribution, with a given cutoff, and then at low energies, it flows to something very broad. So this separation of angular and radial variables is extremely useful. In fact, we can numerically calculate the correlations of the two variables. They are uncorrelated at low energies. Therefore, it makes sense to talk about these angular fixed points at the same time that we have infinite disorder for the radial variable that I'm not showing here. So the radial flows to 0, but the angle flows to a fixed point. And
sorry, Victor, the case theta equals pi over 4 is special?
the point pi by 4 has explicit SUN symmetry. It is also a fixed point. So theta star equals to pi by, if you start at pi by 4, you don't flow, the angle doesn't flow. The R variable flows, the angle, all these points of SUN symmetry here are also angular fixed points. If you start there, you don't flow, but they are, however, unstable. If you start, if you put deviations, you flow away. So you flow to either this theta star equals to pi by 2, theta star equals to 0, theta star equals to minus pi by 2. And this phase here, I will not talk about. It's a ferromagnetic, it has ferromagnetic instability. So I will not be talking about this phase today. This requires other description. But the flow, the angular flows looks like this, what I'm representing by the red. Maybe I should also point out that these points here are stable. These points are also stable. So it flows to points that do not have explicit SUN symmetry. And this comes now I can characterize these angular fixed points here and here, let's say. And starting with this theta star equals to 0, I can characterize for theta star equals to 0 both the ground state and the low lying excitation. So let's see. We have a chain that looks like this. Okay. And then at theta star equals to 0, we get singlets again, random singlets of this form here. For theta star equals to pi by 2, we get different types of singlets. The singlets are no longer formed by only a pair of spins, but instead of 3 spins. So there are singlets like this. They don't have to be neighboring spins, neighboring singlets. I'm just drawing them like this. And in both phases, we can also characterize physical quantities, for example, susceptibilities. So the susceptibility here will be 1 by t, 1 by log t squared. And here it's going to be 1 by t, 1 by log. Here I should be careful to make it dimensional. There is a t0 here. I mean, to make the log dimensions, log t cube in this particular phase. So we can characterize susceptibilities of both phases and all the other physical quantities like specific heat, spin-spin correlation functions, and all of this. But what is remarkable is that both these cases, they still present emergent SUN symmetry. And the conclusion that these phases present, both phases present emergent SUN symmetry coming from, this conclusion comes from 2 points. The first point is that the singlets that we form here, the singlets, do not depend on the angle. So the SON and the SUN singlets are the same. If we start with this point and we solve the problem here, a point that has explicit SUN symmetry, you're going to get the soup of singlets. If you solve the problem here, even though the flow is to a different fixed point, the same soup of singlets will appear. The singlets are independent of the angle that we have in this particular bond. Let's say here we have a given angle, theta 0 and theta 1 and so on. But the singlets are the same. It's just these are SUN singlets. So this is true in both phases. So this is the first, is that the singlets are angle independent. And as a matter of fact, they are SUN singlets. And the excitations are just free, are free spins. These are free spins that also transform under SUN. So again, there is no distinction between this explicit fixed point and this fixed point, even though the microscopic model at these fixed points here that I'm representing in black, the Hamiltonian does not have explicit SUN symmetry, it's SON invariant, but the low energy physics is completely SUN invariant. That's how we can get emergent symmetries in disordered systems. It's a mechanism in which at least for this particular case, you have the ground state and the low-lying excitations being also SUN invariant. And this is generic for this SON chains. It's also true for other symmetry groups like SPN and so on. Emergent SUN symmetries are going to appear in for several different Lie algebras in terms of mathematics. If you write down spin models that are invariant under some Lie algebra, it is often the case that you're going to have this emergent SUN symmetries for the reason that I just explained.
Victor, I have a question. Then what is special about pi over 4?
Pi
Because
over 4.
You have different exponents there.
You
Well,
don't, the exponents are the same.
Well, you have different, no? You have log cubed and the other is log square.
Oh, I'm sorry. This guy, maybe I wrote it wrong down there. This guy has the same exponents as this guy.
But you wrote below, you said.
Oh, maybe I said it. Mm-hmm.
Yeah, when, oh, pi over,
yeah.
Oh, so pi over 2, not pi over 4.
Oh, no, the fixed points are theta equals to 0 and theta equals to pi by 2. Okay, at theta equals to pi by 2, it has the same exponents as pi by 4. Okay, it has the same exponents as pi by 4.
Okay, wait, but so you have a flow towards pi over 2, which is stable at pi over 2.
Right.
You have a flow towards 0, which is stable at 0.
Yeah.
So pi over 4, in some sense, represents phase transition.
Yes. And here, this is something that I was talking before. And here, there is an obstruction to this flow here. This is where this AKLT point is. So you don't flow in this region. So that's how geometrically this is separated from the rest. So here, instabilities in this direction that goes in this particular direction, they flow to pi by 2. Instabilities that go to this direction here, they are harder.
But if you start exactly at pi over 4,
mm-hmm.
then you don't flow.
You don't flow. Then you don't flow.
Okay,
then
so, and what is the behavior exactly at pi over 4?
The behavior is the same. The exponents are the same exponents as pi by 2. And the ground state is, the singlets are also going to be, the structure is the same as at pi by 2.
I mean, naively, I would have expected that point to have higher symmetry than the stable fixed points.
That's right. So that is why this has an emergent SUN symmetry. The low energy physics of the pi by 2 is indistinguishable from the pi by 4.
But the question is, at pi over 4, I would have expected to have more symmetry than at pi over 2 or at 0.
Right. That's right. So that's why
you're saying it's not?
No, the bare Hamiltonian, the explicit Hamiltonian at pi by 4 has SUN symmetry.
Oh, it's already there.
It is, yes. Here it has an explicit SUN symmetry at pi by 4. Okay, at pi by 4.
Which is broken infinitesimally away from there.
That's right. But then it's restored by it's restored at low energies.
Okay, I understand.
Yeah. So the high energy physics will remember that this explicit the symmetry is no longer there, but the ground state and low lying excitations are present there. And we make this, have this analogy with high energy physics where we call this one a mesonic phase, because in the SU3 case, let's say SO3 that has an emergent SU3 symmetry, we can say these are quarks and antiquarks, and then here we can say that we have a baryonic phase in the sense that you have 3 quarks forming a singlet. Okay, this is what we call the mesonic and baryonic. This is the best analogy with this is in the case where n is equal to 3. And this is for, again, let me emphasize this point that for n equals to 3, this is SO3 that has an emergent SU3. And the realization of this, the simplest realization is in terms of spin 1 chains, which will have dipole and quadrupole couplings. All right, not only dipole but quadrupole. Then we can just quote this phase diagram here. This was actually our first work. our first work was, well, let's look at spin 1 chains. And then we discovered that it was looking promising. And then we said, well, is this an isolated case? And then we discovered, no, actually, the way to think of the spin 1 is not as a higher representation of SU2, but instead as the ground, as the fundamental representation of SO3. And we were recently able to generalize it for arbitrary n. So this is my work from 2019. Okay.
Sorry, again, for general n, the variance contain n quarks, right?
That's right.
So not 3.
Not 3. They will.
So is that what happens here? Get some kind of clustering going on?
Yeah, that's right. So to answer more or less mathematically is that you need in SUN, you need any n. So let me write it down. So for in SUN, you need basically n spins to form a singlet. This is a possibility of forming a singlet. You can form a singlet in SUN with either 2 spins, can form a singlet in SUN, or two, one in fundamental and one in the conjugate anti-fundamental rep, or any spins in the fundamental rep can also form a singlet. So you have this clustering effect. For SU4, for example, we would represent this is a singlet of SU4. It's 4 fundamental reps of SU4 merged to form a singlet.
Okay, thank you.
Right, you're welcome. So just to wrap up, future directions. There are several possibilities to explore. Just to very quickly mention 3. Also, I'm interested in studying these emergent symmetries in clean systems. So I have collaborated. I have collaborations to understand, like, now to transition instead of having disordered systems to understand clean systems. The tools are different and all of that, but I'm moving in that particular direction. I think these emergent symmetries are quite interesting. Another possibility, and this one comes directly from this strong disorder IG that I showed you, is to look at excited states, emergent symmetries here. Another possibility is to look at excited states within this strong RG procedure and look at, for example, many body localized phases. These are phases that require description in terms of excited state, not low energy physics, but also excited state physics. And also, and one of the main directions that I'm starting to work on is this RG, but with fermions that are disordered and interacting. Hubbard model, for example, disordered Hubbard model types of physics with this type of strong disorder RG. There are some challenges involved in this approach number 3, but we are making progress recently to characterize quantities like conductivity of this random, of this disordered fermionic systems. So these are future directions that I'm planning to work on in the next months and years. So I think that's what I had to say. So thank you very much for your attention, and I'm open to other questions.
Thanks very much. People have questions?
I have a question. I don't know if you have thought about entanglement. There is a result that is worked on these strong disorder fixed points, so in the random singlet phase,
right,
by Raphael and Moore,
right,
where they showed that in these one-dimensional strongly disordered chains show this logarithmic scaling, which is characteristic of a CFT. But with a prefactor that is not entirely clear what the interpretation is. It's universal, as in the case of the CFT, but there is no central charge that anyone has ever been able to find. And because it's a disordered system I don't think this is totally well characterized. But the prefactor is also universal. It does depend on the structure of the random singlet, I was wondering if you have thought about that, and in particular, as a way of distinguishing this baryonic from the mesonic phases and so on that you're discussing here.
Yeah, so the way to calculate the entanglement is basically by making a cut and counting the number of spins that are, or the number of singlets that are crossing, that are the number of bonds connecting spins, forming singlets that are crossing this bond. I thought about it.
Sorry, I think it's more like an interpretation, this one, if I remember correctly.
Well, no, they do it. Okay, so they do this. They run this RG and they calculate the flow of the entanglement entropy.
Right.
Okay.
And the flow of the entanglement entropy comes from counting the number.
That's how they calculate that. It's true.
Right.
But,
yeah, I didn't think about how to interpret this, especially the prefactor. I'm not sure if the prefactor would be the same in this case. That's a good question. I don't know. I would have to think.
Because in particular, you are saying that some, the susceptibilities appear to be the same.
Right.
And the question is, what distinguishes these fixed points apart from the value of theta? So you're saying one is mesonic, the other is baryonic. I'm not entirely sure what observable will distinguish them.
Yeah, the exponents of susceptibilities are different for baryonic and mesonic.
Oh, they are different.
They are different.
Oh,
yes.
this is the cube, the cube.
The square and the cube, yes.
I see.
But I think it's a great question in terms of, I will think a bit more about, I looked at it and I concluded that the log would be the same as in the case of Raphael and Moore, but I didn't look at the prefactor very carefully. It's a good question. I would have to think about it.
So can I ask a quick, let me see if I understand. So here we get an emergent symmetry because the interesting, the things that are not free form singlets, so they kind of disappear. So they are blind to whatever symmetry, right? They are singlets, so they don't have any, they are singlets. And what remains, you just count how many there are, right? And because there are n and they are a vector, you can call them SON or SUN, but it's just n free things, right?
That's right. That's right. That's precisely, yes, that's it.
Okay.
Yeah.
So in that sense, even though there is this symmetry, it's a little bit. It will be more interesting if there were interactions remaining, and if the interactions would have more symmetry than the original. And it will be more mysterious, right? Otherwise, it is just saying that something freezes, the rest is free, and free. Am I right?
This initial system is strongly interacting. So it's, in some sense, a remarkable feature that at low energies, you have some excitations that are just free spins, even though it's a strongly disordered interacting initial system. And also, I would point out that the fixed point pi/2, where this flows, does not have explicit SO3 symmetry. It's not, even though in the beginning I gave this picture where I had a fixed point, and then this fixed point, I have irrelevant operators, and the irrelevant operators flow away. In these disordered systems, it's slightly more subtle in the sense that it flows to a fixed point that the bare Hamiltonian, if you write down the bare Hamiltonian at this particular point, it does not have SUN. But
you mean the clean one, right?
The disordered one as well. A global SUN. These are, I'm talking here all about global symmetries of the disordered Hamiltonian. It's not a local, in the sense that if you
mean for a given realization
for a given realization, yes, that's right. And in that sense, this fixed point does not have the explicit symmetry if you write down a Hamiltonian or a microscopic model, but the structure of the flow is such that because of these singlets, because of these free spins, the symmetry is enhanced. So it's,
yeah, maybe I'm naive, but it looks exactly like what you said. So that is very non-trivial, that you start with a system that's very strongly coupled, and then you form these dimers or baryons or whatever, right? And then somehow the remaining dynamics are just a bunch of free particles moving in that sea. So that is super cute and very non-trivial. But now the fact that they have SON or SUN, I mean, isn't it just language, because they are free anyway? So I mean, it's n free guys. Who cares if
Well,
Well, they are not totally free. The logs come from this. In a sense, they are like corrections scaling. Otherwise, it will be just 1/t if they were truly.
right. No, but I think the comment is about when we get this 1/t, we get it because it comes from the number of spins, but the number of spins that are free, but not all of them are free. But it is true that the emergent excitations are free spins, yes. But yeah,
But they are not truly free in the sense if they were truly free, will be just Curie wise.
no, but not all of them are free. Some of them are frozen into singlets, and some of them are free.
I have a silly question. How do you distinguish a fundamental from anti-fundamental?
You mean in terms of constructing the chain?
Yeah, well, how does the SUN act? I'm just asking a stupid question, but I mean, how does the one of the SUN act on?
Right. So I usually represent the fundamental like this. Let's say for SU3, and the anti-fundamental is going to be like two boxes here. You can conjugate. Some of the generators are going to be conjugated, and then with these two guys, you can already form a singlet. So in terms of how to construct it, some of the operators here are complex conjugates of the fundamental EREP. And in terms of the angles, they are going to appear for different angles.
Okay, I think you answered my question. Okay, thanks. Roger, you had a question?
Yeah. So can you say that the symmetry, the emergent symmetry, is a global symmetry, and that the original symmetry was a local symmetry? Is that correct?
No, both of them are global symmetries.
Both of them are global symmetries.
Both of them are global symmetries. Yes.
Because I was thinking, do you know an example? So I was thinking in terms, say QCD, right? In QCD, you have at high energies have quarks and gluons and an SU3 symmetry. And when you go down in energies, you have confinement, etc. You change the degrees of freedom, and then you have SU3, but it's the old eightfold way SU3. Is this the same idea, or is it different from what you're?
No, it's different. We don't have gluons. We have some differences.
No, I know. But the idea that you start with a symmetry and at low energies have another symmetry.
Right. This is a generic. Yes, but this one, the difference is that this one is not local, but the idea is, yes, it is the same idea.
But then, so it starts with symmetry that is not global, and it's global, and then you end with symmetry that's also global. So the interactions that you have in the beginning have nothing to do with gauging the symmetry, let's say.
No, nothing to do with gauging the symmetry, no.
Okay, thank you.
Nothing here is gauge symmetry. It's explicit SON symmetry of the Baire Hamiltonian, explicit or emergent SON symmetry of the low-lying excitations, and
okay. So
nothing about gauge.
Okay, Victor, just so as a particle physicist, I'm used to the opposite thing, that when you go to high temperatures, you increase the symmetries, and when you go to low temperatures, you decrease them. Do you know any examples in field theory where you go to high energies and increase this and you decrease the symmetry?
You go to high energy and
in particle physics or field theory.
Decreasing the symmetry at higher energies. Let me see. No. Usually at high energies, even in like when I go this matter physics block, usually it's the particles become more free as you increase the energy, and you melt a crystal and then recover it from their symmetry. Like Kondo effect, the spins, the localized moments become asymptotically free, and so on. So
right,
I'm more familiar with.
In some sense, this is unusual, right?
It is unusual, yeah.
Well,
there were examples, right?
There are other examples of this.
Yeah.
The edge states, for example, of multi-component quantum Hall fluids, particular ones with propagating and counter-propagating modes, have emergent higher symmetries of this type due to disorder. In the clean system, the symmetry is lower, actually. It's a tensor product. But the distribution is more symmetric in the asymptotically. But there are examples of one-dimensional chains that do, I mean, for instance, people try to construct at one point an SO5 symmetric quantum spin chain. and it turns out that actually had an emergent SO8 symmetry, so, which was the opposite of what they expected. So there are examples, but they are not. This seems to be generic in disorder systems.
Right.
Okay, thank you.
There were also examples in field theory. Remember, Gustavo Lozano was working on this when he was in Trieste with Giuseppe Bimonte. And in field theories, they had examples. If you wish, I can send you some references later on.
Oh, thank you. I'm not familiar with the case where the high energy or high temperature phases are less symmetric.
The keyword was symmetry restoration. That was the keyword at the time. There were papers from, I'm looking at end of the 90s.
Okay, thanks.
So in a sense, this is the opposite of fluctuation-driven symmetry breaking, essentially. This is actually enhancement, it's not reduction.
That's right, that's right.
So this is...
You have a question?
Yeah, so I'm just out of curiosity. Do you know if it's possible to investigate this type of emergent symmetries in cold atoms? Because they realize SUN chains.
Yes, I'm not familiar with disordered cold atom setups so far, but would be very happy to discuss it, because I was thinking about it. What is the minimum size that you need to realize and to see this? Because this is it's an emergent low energy property. It would depend on the initial distribution of how disordered the cold atoms are. But I think this is a very interesting possibility. I'm not familiar if this was realized, but then it becomes, because even though the physics here is universal, it takes some orders of temperature to reach the fixed point. So I'm not familiar if this was actually implemented, but
no, I think in that case SUN was clean.
Right, but then this in that particular, I'm talking about this particular case because it turns out that there is this algebra isomorphism between SO6 and SU4. So in principle, if you start with SU4, an SU4 system, you end up with an emergent SU6. So this one is would be a possible relation by this isomorphism between SO6 and SU4.
Yeah, there are examples of random chains done with cold atoms. They were used for something else. The problem is that in the cold atom setup, it's very difficult to measure local susceptibilities, which is what we are accustomed to. So you will have to look for other signatures. The susceptibility, I don't think they have any real way to measure that.
Okay. But sorry, I think that probably this is related to point two of your future, because probably it would be easier to do it in a kind of dynamical experiments in the long time, like a quench, and then look at long time if they can measure it.
Yeah, this is right. I think, yes, in particular, yes, the excited states, this I was thinking more not only about emergent symmetry, but to understand the physics of this, what is called many body localization physics. This is a different direction, but in terms of the experimental verification of these emergent symmetries, I would be very happy to discuss about how the possibility of doing it experimentally. I think cold atoms probably are, even though there is this issue with measuring local susceptibilities, I would be very happy to discuss it.
Or can I have something? So point one looks very different from the rest of the talk, right? So here this order was super crucial.
About these points here,
point one seems a bit
okay, yeah, no, it's just
disconnected, right? This order was so important. So what is the idea without this order?
So we recently, when I was studying this, we came across this case of spin 2 chains, and these are spin 2 chains. So that's got my attention. So spin 2 chains that have an emergent SU3 symmetry. So these are SU2, an SU2 problem. These are SU3 symmetry. And even though and these I have collaborators that are experts in clean systems, but it's unclear how this symmetry enhancement actually happens for this spin-2 chain. Because in phase diagram, there is not a point with explicit SU3 symmetry. So if we look at this picture below here, in this picture, we assume that there are some irrelevant operators that will go away at the low energy fixed point. That is already different. This is what I had in mind clean systems. This is already different from what I showed in disordered systems. That is not exactly like this. But this case is quite intriguing because there is no point of SU3 symmetry in the phase diagram. So, and this was conjectured in 2015 by Shannon and collaborators to be the case. So we started investigating this, and we are running some numerics and try to, with collaborators, to even write down some field theory that would, in principle, describe this emergent SU3 symmetry. Many of the group theory tools that were used here apply for this case one. So that's the one I'm interested the most about, this emergent symmetries in clean systems where you can use this Lie algebra apparatus that I also use. So this will be the connection in terms of these higher symmetry groups. But the tools are very different.
I mentioned before, there is an example of that people tried, Suchen Zhang and various collaborators a long time ago.
Right.
They tried to construct an SO5 symmetric system, and it turns out they had an emergent SO8 symmetry, which was driven by quantum fluctuations in a sense. But that's, so in this case, the SU for the spin 2 will be a gap state, right? There is no criticality in this case.
No, it would be SU3 level 1 critical.
Sorry, but SU2, this SU2 spin, if you have SU spin 2, SU2 spins, which.
No, but we have a quadrupolar, octopolar interaction. So the phase diagram, we include not only the Heisenberg S.S term, we have S.S squared, S.S cubed, and so on.
Okay, so you're saying that there is an additional fixed point that actually has SU2 symmetry.
So the chain has explicit SU2 symmetry from the beginning, but it just has these operators here, S.S squared.
Okay, so this is the analog of the spin 1 fixed point, which is SU2 level 3?
Yes, except that in spin 1, you have the point pi by 4 already has SU3 explicit symmetry, right? In this case, what we don't have is a point where we have explicit SU3. That is the mystery. This is just this is my point was just to mention one possible project with collaborators about clean systems using this group theory structure. But to be explicit about the difference is that this spin 2 chain does, so in spin 1, so just to answer more precisely, in spin 1, if we draw the clean phase diagram, so we have S.S and S.S squared. So we can write D and J here. And then we can draw a phase diagram. There is a point here, pi by 4, that has explicit SU3. And then this phase here is critical. This phase here.
Yeah, it's SU2 level 3, which is dual to SU3 level 2. Okay, it's equivalent. And there is level rank duality that you're using there. But the symmetry is SU2 level 3. This was established by Affleck in the 80s already. Okay. There is a duality that you can use. So imagine that for SUN, there may be an SUN level 2, which is equal to SU2 level n.
Yeah, we couldn't find that. We tried. We couldn't. Yes. Yeah, we couldn't. This is exactly the type of the line of work that we couldn't find this level rank duality still for to get this SU3 level. But just to the broader sense, this is why these emergent symmetries in clean systems using group theory. I think these are very interesting, and we had it with with using the disordered system. So I got excited about trying this also in clean systems as well. But the tools are indeed very different. Points number 2 and number 3 here are more related to the. So this point number 1 is related to the emergent symmetries, and points number 2 and 3 are related to the strong disordered cases or systems.
Any other questions for Victor?
Not from me. Thank you for a nice talk. Really nice talk.
Thank you.
Okay, thank you, Victor. So, okay, so I guess the local faculty will meet with Victor tomorrow at 5. I'll send you guys the links.
Sorry, can I ask,